Yes, I have everything. Huh? Yes, I think it's. We wait for Paulo or. Ah, photo? Here? It's okay. I don't know if. Yes, yes. No, no, yeah. Yes, in Butukatu 3 times, yes. Okay, okay. Thank you very much, Paulo. In RIA, it's the National French, French Institute in Research in Computer Science and Automatic, but our team is in applied mathematics. And the name of the team that I am working on is Dracula team. The name is because we are interested by modeling blood cells. This is why we call the team Dracula team. Dracula team is we are about 20 person. It's okay. And I am a mathematician. In our team, most of us are from mathematics, applied mathematics. We work in cell population dynamics, multi-scale models, and especially we are interested in hematopoiesis, which is the process that leads to the production and regulation of blood cells in the bone marrow. I will have the opportunity to show you some models that we are working on. Okay, and especially we use delay differential equations to model this kind of biological process. It's okay, Paulo. He's up. Okay, I will give you an introduction to delay differential equations, and please not hesitate to interrupt me if you have questions or about something that you didn't understand, or if you want more precision about something, don't hesitate to interrupt me. I use these references. They are the main references in delay differential equations. The book of Kwang and Hale are more theoretical, and this book, I think it's the more adapted to applications. And I will use mainly this book to give you an introduction to delay differential equations. Okay, there is many chapters. The first one is a real introduction to delay differential equation. After that, I will talk about stability of steady states. I will talk about also Hopf bifurcation, maybe about also global stability and Lyapunov functions, and with many applications. And also, of course, some results about existence, uniqueness of the solutions, global existence, and also local one. I start by an ordinary differential equation to introduce delay differential equations. We know that many process, modeling many process, we generally assume that there is between the actions and the reactions, it happens in the same time. You take an initial condition like a point, t0, x0, and you solve your ordinary differential equations on the right of point t0 or on the left also. And if we consider, I think this is the first model that was introduced for in ordinary differential equation it was Malthus model, which describes the evolution of a population of individuals. If we denote by capital N of t this population, and we consider uh, the birth rate given by B and the mortality rate given by D, and we consider this sample process, we obtain this simple ordinary differential equation. And this one, it's if we take an initial condition n0, it's very easy to solve. I will start with this and introduce delay to show you that the behavior of the solution will change a lot, too much. There is a big change if we take this simple ordinary differential equation, or if we add a delay, the behavior of the solution will change too much. Okay, this Malthus equation can be solved easily. We obtain exponential solution, and we have three situations. The first one, if you have B greater than D, then the population will grow exponentially to plus infinity. And if you have the mortality rate bigger than the birth rate, you will have also exponential, but now exponential decays. The population will go to 0 and disappears. And if you take the rate B equals to D, the population will remain constant. Okay, if we consider, and now I will explain why we add the delay here, and why also this parameter C, in the first model it was B, and now we have this another parameter. We have to change the parameter here. We add here a delay, and which is positive. And this delay, it was introduced, for example, for this model by Cook and York. They consider the Malthus model, by which is only adult population, and they add this delay. Why? First, we consider only adult population because, let's say, for example, we take R equals to 18. Populations cannot produce another individuals before 18. You have to wait until 18. This is why we have this. That means the population that comes from adults, in fact, they come because we have to wait until this new population becomes adult. Then we have to wait 18 years, and this is why we take the population at time t minus 18. And why we take here this parameter C different from B? Because this population, if we assume that the rate of mortality of this population is the same as the adults, as the adult people, we have to take only the survivor population. And as D is the mortality rate, then the rate of surviving is given by this this expression, the exponential of minus TR. Because the contribution of individuals to dynamics of the population is not instantaneous, but you have to wait until this population become adults. Many models has this the same explanation by adding delay, but I will show you next time, starting with age structured model, and to reduce it to a delay differential system. It's not only adding delay like that. Here we have to be careful adding delay in a system, because the parameter changes, and it's not true to add the delay in an ordinary differential equation like that. to have to model a phenomena, you have to take care about uh, this thing. Okay, we can add the delay in ordinary differential equation and becomes delay. I will first, before that, I will show you that the system is, or the equation that we obtain, it's completely different from the other one. This is only to say that it is a delay differential equation. It's not ordinary differential equation. And for this case, this is a discrete delay because there is only one delay, and it is not distributed. It's at each time you need to know the solution at time t minus r. This is why we call it discrete delay. We can okay, we can say let's try to solve this delay differential equation using only the ordinary differential, the things that we know about ordinary differential equation. Let's take this one because it's more easy. And we put for t equals to 0 this initial condition. Okay, and try to solve this system. It's very easy to show that there is at least two solutions of this ordinary, this delay differential equation, considered as an ordinary one. And this is never happens for ordinary differential equation, especially in linear case. And here we are, that means we have two solutions, and the solutions can cross all the time. They are infinite. We can prove that there is infinite solutions of this ordinary. You can try to show that these two functions satisfy this differential equation. That means there is no uniqueness in the classical sense. That means we cannot consider this delay differential equation like ordinary one. It's not true. What is the problem for this? What is the mistake? Can someone? What is wrong here? What is not good in this? It's this ordinary initial condition is not good. We cannot take initial condition on one point. It's not enough to solve because if you take here t equals to 0, that means you can take t equals to 1 to solve the system. But if you want to calculate the derivative for t equals to 0, you will need to know x on minus 1. Okay, then you have to add it also, because it's, if you want to define the derivative for t equals half 1, you will need to know x on minus 1 over 2, etc. That means at the end you will need to know the solution on an interval of length equals 1 to solve. And this is the difference between, that means the initial condition is a function defined on an interval of length equal at least the delay. Okay. I will take again this, and of course I show you that it's not, the problem is not well posed if we take an initial condition on one point. It is not enough to solve it using this. But in addition to n of, I will start here from t0. To solve the system, in addition to n of t0, we need to know n of t0 minus r to solve the system on the interval t0, t0 plus r. We need to know the solution on the interval before, that means t0 minus r, t0. And therefore, the initial condition has to be, as I told you, has to be defined on to solve the equation from t0. We need to know the initial condition on the interval t0 minus rt0. In that case, if you take the system and you take this initial condition on this interval and you want to solve it on the right of t0, then you can, if we can do it step by step. If we take t in the next interval, t0, t0 plus r, if we take t minus r, here you will have this function. That means for t in this on this interval, the ordinary the delay differential becomes this one, and this is an ordinary differential equation because we know this initial condition and we have to solve, and then by we can solve this ordinary differential equation by the variation of constant formula. Everyone know this. If there is something, this variation of constant formula, we solve first the ordinary differential equation without this non homogeneous part, and after that we make like a variation of method of variation of constant formula to solve it, adding this non homogeneous term, and then we have this this solution. And this solution is explicit because we can compute it in terms of this function that we know here and here also. That means we have explicitly the solution of the delay differential equation if we take an initial condition on the interval t0 minus rt0. But it's not finished because now we know the solution on this interval, then we can solve on the next one. Then we continue like that on the interval t0 plus r, t0 plus 2r, etc., until we find the solution on all the interval t0 plus infinity. Okay, that means Cauchy problem means differential equation plus initial condition. This is what we call Cauchy problem. That means for delay differential equation, the Cauchy problem is to give an equation and also an initial condition defined on an interval of length equals to the delay. Okay, and after that, of course, now we define what that means solution. We can, after that, I will show you that the Cauchy theorem is existence uniqueness of the solution coming from ordinary differential equation can be generalized to delay differential equation without problem. I will give you now some examples of delay differential system. The first one is Volterra because it's the most famous one, and I think it's the first one. Volterra was the first one that he introduced delay differential system, and he considered a predator-prey model. You have two populations, and one are the number of preys, and N2 the number of predators, and you have the evolution of the preys. This is the birth rate, and this is the mortality, which depends, the death rate, which depends on the predator. You know, because the predators kill the prey, and we use this function. For the population of prey, this is the mortality rate, but the birth rate depends, because how to explain that the evolution of the predator depends on the population of the prey on an interval of length equals to r. If you take here t equals to 0, it's only to c, you take t equals to 0, that means the evolution of the population of predator depends on the consumption of the population of prey on all the interval between minus r and 0. To explain this, for example, if we decide to add prey, population of prey in the system, the population of predator will not increase immediately. It's not possible. You have to wait a certain time to have this evolution. We cannot, if you add more prey, the population of predator will not have to wait until to have other kids and to grow, etc. It need time. But and the opposite, if you add, if you increase predators, the population of prey will decrease immediately because they will eat immediately the prey. This is why here we don't have delay, and here we have a delay. Delay here, it's a time to take into account the consumption of the prey and to evolve. This is why the predator birth rate here is assumed to be dependent on the prey consumptions over the time interval t minus r t. Here we choose to take the difference. This is also delay differential equation, but it is different from the other one because it's not discrete delay. Here we call it distributed delay because you don't need each time to know the solution at time t minus r, but you need to know it in all the interval each time. Each time you take here t equals to, for example, t equals to 0. If you put here t equals to 0, you have minus s. S is between 0 and r. That means you need n1 between minus r and 0. And to have the derivative at t, you need to know the solution between t minus r and t in all the interval, not only at what point, but all the history of the solution on this interval. This is explained here. Okay, of course, there are, as I said, this system is a delay differential system with distributed delay. And the description of the state of the system at time t needs to know the solution not only at time t minus r, but at all the set of states of solutions between t minus r and t. Also, Volterra considered we can this system it's distributed delay, but finite distributed delay. We can have or bounded distributed delay. We can have also unbounded delay. That means you need to know the solution for all the past from minus infinity until 0. And you have this kind of system. It was also introduced by Volterra, and this is also predator-prey system. Of course, this is here when you take plus infinity, of course, the function k must be, for example, when you are near minus infinity to go to 0 to have something correct. Another example, it's also famous. It's a system of neuron activity. It was introduced by Marcus and Westervelt, and now there are many systems studied by many people in this kind of fields. And the first one, it was this one introduced by this guy. X of t is the electrical neurons activity, and the delay here represents the delay of transmission between output and input. This function is hyperbolic tangent function. It's defined like this, between -1 and 1. Okay, maybe we will come back to this system. We can also consider the dynamics of n neurons, a big network with here when this coefficient is equals to 1, that means there is no self excitation with the same neuron. If if you take it equals to 1, there is excitation, if you take it 0, the same neuron cannot excite himself like for the first one, where the coefficient here is equal to 1. This is also, we can see this is a nonlinear function, and we have what we discrete delay also, but this one we have many discrete delays. Then we can have this kind of this is a system, of course, and you have many discrete delays. But the theory and all the things that we will do for one delay can be easily translated to many delays. The only part that are not easy, it's distributed delay. It's different from discrete delay for many results. I want only to say something about this equation. When, for example, if we look for a constant solution, that means independent on the time. Independent on time, you will have here constant. Okay, here also you have the same constant because the time is the same. And here you will have 0. That means what we can call constant solution satisfied alpha x equals tangent hyperbolic of x. And it's something, it depends on if alpha is less than 1, you have this, you have 3 constant solution. 0 and 1 here and 1 here. And we will see that it depends on alpha. Sometimes you have this point attractive. That means all the solution will go to extinction, or this one, or this one. It depends. In general, this one are unstable, and this one is stable. Attract the solution for this this kind of system. We will come back to this if we have time. Of course, there is for logistic model also we can add delay and change the system. It was done by Hutchinson. Let's start with the classical logistic ordinary differential equation, this one. And all of you know that this ordinary differential equation has, we can say, 2 equilibrium. N equals to 0 and n equals to k. And if we take initial condition bigger than k, the solution will go to this steady state. And if you take it between 0 and k, you will have, I think it's like this, yes. All the solutions go to this carrying capacity of the system. It's not difficult to prove. We can do it without solving the system, because uh, we know that when you have ordinary differential equation like that, we have all the solutions are monotone all the time. If, of course, for scalar function, we have only one way. There is no oscillations for this kind of ordinary differential equation. Why? Because if you can do it by contradiction. If you assume that you have something like that, if there is solution doing this, then you will have T1 and T2, and here n of T1, and you will have a contradiction because the system is monotone. Why? If you have this, that means the derivative of n1 times derivative is negative, because they are opposite. Okay, and we know that n satisfy the ordinary differential equation. Then we have times negative nt1 equals nt2. That means, and this is a contradiction. Yes, this is why we never have oscillations for ordinary differential equation from R to R, because of this. But when we add the delay, it happens. Here, for this logistic model, we can solve the equation easily by separation of variables, and we obtain this solution. And we have if n0 is less than k, as we know that the solution is monotone, it's in general it suffices to take the initial condition. If the initial condition is positive, it will stay positive. The derivative is positive, it will stay positive all the time. If it's negative, it will stay negative. This is why we don't need this. It's very easy to solve, to know the behavior of solutions for ordinary differential equation. Here, if the initial condition is less the carrying capacity, the population will grow and go to k. And if n0 is greater than k, the population will decreases and go to k. And of course, if n0 equals to k, the population remains constant. In fact, we have this equilibrium k is which is the positive equilibrium, is globally stable. What that means, globally stable? You can take initial condition positive as you like. Everywhere you will go to this steady state. Then we say that this steady state is globally asymptotically stable. Of course, in this system, and in general, when we have a population with carrying capacity and etc., in general, the population will not grow all the time. There is all the time fluctuation. They go, they pass the carrying capacity and decrease, etc. And the only delay differential equation can explain this, can give this kind of behavior, and never ordinary differential equation in, of course, one dimension. I'm talking only about one dimension. For this system, because the logistic model, we assume that the growth rate depends on the number of individuals using this expression. As for the others, because we know that in practice, the reproductive process is never instantaneous, because there is like a period of gestation, or for eggs, we need hatching time. It's not instantaneous. When you are eggs, they will not be adult instantaneous. You need certain time, and sometimes it's very long. this time. This is why in 1948, Hitchinson proposed to take into account a delay. He was studying egg hatching, and he proposed this model. This is the same. He keep the carrying capacity. Yes, he keep the carrying capacity and the growth rate the same. He changed only here by adding delay. And then we obtain this a new equation that which is called Hitchinson equation or logistic equation with delay. And this is also no linear one. Oh, this is also a very famous model. It's the blowfly, Nicholson blowfly model. Is the same explanation by adding delay here, both here and here. It was in 1954. Nicholson, he was studying the fluctuation of this blowfly, and he because he tried to use ordinary differential equation, it doesn't work, and he has the idea to use a model with delay that gives him explain him the fluctuation that he observed because he had data, and he want to fit data, and it was the best equation to fit data. Why we add here delay is the same explanation, because the blowfly gives eggs that become larvae, which become mature, but all this process needs time. And he assumed that eggs and larvae take exactly our time units to develop into adults. And here he considered only the population of adults. Okay, he escaped the process of immature blowfly. You have something under here, and this is given by this expression. That is why there is a delay. The new adult should be, this is the explanation, regarded as a productive product of fecundity, which is given by this expression, and also a probability of survival from immature to adult flight, which is given by this expression. This is the survival rate, and this is the fecundity rate. And the probability of survival, of course, decreases if we increase the population, because there is like competition for foods for immature blowflies. And this until now there are many until now open question about this simple. This is why it's very famous. If you by Google you type Nicholson blowfly equation, you will have like hundreds of. This is very simple, but until now we are not able to prove the global stability of the steady state. We prove only a part of this global stability for some parameters, but not in general. And we are sure that we have global stability. Yes? This is a discrete delay. Yeah. Yes, exactly. Yes, exactly. Exactly. We take in general distributed delay because it's like sometimes it can be approximation. For example, we can say for humans, we know that the gestation period is 9 months. We can say it's 9 months. Sometimes it's not exactly 9 months. It can be maybe between, yes. But in that case, we can say, oh, it's a good approximation to take 9. But other population like mosquitoes, for example, it's not exactly the X can. It depends on the temperature. It depends on the humidity. It depends. In that case, you cannot say they will hatch at this time. And in that case, you can take like distributed delay depends on the temperature and many things like that. We find also delay differential equation in epidemiology. For example, I think all of you know this kind of SAR model. It's okay. This was studied by Van den Driesch in 1994. It's a SARIR model with delay. We have 4 classes of population: susceptible, exposed, infected, and removed. Why this is we can say the new things in this model is the exposed, because for tuberculosis you can be exposed, you can have the disease but not yet infective, and you need 9 months to be infective. This is why we cannot consider this population as I. This is considered separately. To explain this is of course the recruitment. This is the natural mortality. This is the infection. The force of infection is given by beta. This infection people, but they will not go to this compartment, but to this one. Okay, this is the new infection population. This is the mortality, and here the difference is. Let me explain. I don't remember how to. Yes, because the system was before partial differential equation with age and transform to this. Okay. Yes, this population come here and we take off this because they will go to this part, but we have to wait like 9 months, and this is the survivor rate in the exposed population because the mortality rate is given by mu, and the time, the duration of this compartment is exactly tau. Then we take them from here to put them in, because they become infected. This is why we have this population, this flux from exposed to infected population. And this is the removed population that go to the compartment R. This is another also SIR epidemic model with the delay. Here we consider the immunity period because you have the same, and the duration of the immunity period is fixed. That means S is susceptible, it becomes infected, and yes, becomes infected, and yes, and the duration of the infection is omega. They are removed, and after that they become susceptible because the immunity is fixed. It's not forever. Then we take them from population of infected to becomes again susceptible. and they stay in this removed class exactly omega time. We will see, because this system has a problem for positivity. This is why I put here there is a problem with R. We need conditions to show that R is positive and cannot become negative. This is also a famous model of Busenberg and Cook. It was introduced in 1978. This one is different from the other one I want to show you, because there is the coefficient B depends on the time, and Y of t is population of humans is normalized to 1 that is infected by disease given by mosquitoes, and C, the coefficient C is the recovered rate. We can okay, how to explain the delay. Yes, we take population becomes infected by mosquitoes, and after that the infect